Look closely at the bottom of this photograph. Those tiny figures are people. Rising directly behind them is the Great Pyramid of Khufu, a monument built from 2.3 million stone blocks, reaching nearly 500 feet into the sky. For almost 4,000 years, no human-made structure stood taller. Putting those stones in place is a logistical puzzle that has lasted millennia. We are talking about hauling individual blocks weighing 2.5 tons for miles across a barren desert. And the ancient builders accomplished this without wheels, without pulleys, and without iron tools. Today, archaeologists face a different version of that problem. We have evidence that undiscovered rooms lie deep inside that massive masonry, but we cannot drill into the rock or use explosives to find them. The structure is far too fragile for any destructive testing.
Understanding how these stones were placed and what they hide now moves in two directions: tracing how ancient builders manipulated their geography and observing how modern physicists use the behavior of subatomic particles. The pyramid sits at the center of these breakthroughs, where the logistics of the Bronze Age meet the precision of modern particle physics. For a long time, the delivery method for the heaviest stones was a blank spot in the historical record. Then, researchers translated the Diary of Merer, a logbook kept by an ancient overseer. His records detail elite crews transporting massive limestone blocks on wooden boats, even though the pyramids sit miles away from the modern Nile River. To see how that was possible, researchers used a satellite scanning system called Tandem X. By beaming synthetic aperture radar into the ground, they peered beneath centuries of desert sand and agricultural fields. What they found was a buried 40-mile-long ancient river tributary, the Ahramat Branch. Thousands of years ago, this lost waterway ran right alongside the Giza plateau. Barges loaded with up to 80 tons of stone navigated the river and entered artificial canals, delivering their cargo to harbor basins at the construction site. But water only gets you to the harbor. From there, teams of workers had to drag those 2.5-ton stones overland on wooden sledges. Pulling a heavy load over dry sand causes it to pile up in front of the sledge, creating massive physical resistance. This data visualization shows how they manage the sand. On the left, pulling a heavy weight over dry grains creates a barrier. On the right, you can see what happens when you pour water onto the path. At exactly 5% water content, microscopic water droplets form capillary bridges that glue the grains together. The friction drops by half, allowing the sledge to glide. The records of Merer describe a workforce of specialists. By mapping river tributaries and tuning moisture levels in the sand, they used the natural fluid dynamics of their environment to do the heavy lifting. The ancient builders mastered the outside environment to construct the monument. Now, modern scientists are mapping the internal environment, looking directly through 500 feet of solid rock. To do it, they use Muon Tomography. Muons are high-energy subatomic particles created when cosmic rays strike the Earth's upper atmosphere. They bombardment the planet constantly, traveling at near light speed, and they are small enough to pass through solid matter. Dense materials like solid limestone eventually absorb or deflect some of these muons, but if those particles hit an empty void inside the rock, they pass through unhindered. By placing detectors beneath the structure, scientists can measure the concentration of surviving muons to find the shadows of hidden rooms. In 2015, the Scan Pyramids project laid out nuclear emulsion films and gas detectors on the floor of the Queen's Chamber, deep inside the Great Pyramid. Then they simply waited for months, letting the pyramid catch the cosmic rain. This data made headlines in 2017. These heat maps show the concentration of muons hitting the detectors. The bright spots at the top indicate a specific statistical anomaly: a high flux of particles passing through an unmapped empty space. This was the first major inner structure identified since the 19th century. By analyzing these three-dimensional coordinate plots, scientists mapped the dimensions of this big void. It stretches at least 30 meters long and sits directly above the known Grand Gallery, a conclusion verified by 3 independent teams. The discoveries are continuing. Recently, these same non-invasive scans identified a hidden 9-meter corridor situated right behind the main entrance. Architects believe it was built to relieve the weight of the masonry above the doorway. In mapping the interior layout, modern physicists mirrored the approach of the ancient builders. Rather than applying destructive force to the stone, they used the natural behavior of subatomic particles to see right through it. Building the Great Pyramid required moving massive natural systems. Ancient engineers mapped the Ahramat River branch and tuned the friction of desert sand. Analyzing the pyramid now requires moving microscopic systems, utilizing ambient cosmic rays traveling from deep space. Neither achievement relied on smashing through physical obstacles. Both teams reached their goals by working with the invisible forces of nature. We are seeing a monument that is no longer silent. The Great Pyramid continues to yield specific structural secrets from deep within the stone. The Great Pyramid remains a physical record of problem-solving, a 4,500-year dialogue between the builders of the Old Kingdom and the researchers of today.